Okay, in this video we're going to talk about motion diagrams, and we're going to do this with an example, which I have an example here. And if you look at the picture on the left, this is a Saturn rocket blasting off, and you can see the red dots here just indicate the position of the top of the rocket at various times, and the time interval between successive dots is always the same. Okay, so this is our Saturn rocket blasting off. To the right over here we have the velocity versus time graph, and these green dots just represent the velocity at these time intervals. Notice that initially it's at 0, and then we increase, and it's fairly linear. I mean, it's a line of best fit, but these dots are almost right on the line. Okay, so what I want to do is draw a picture representing the motion of this diagram. These are very useful when we're solving problems, and I strongly urge you to get used to drawing pictures when you're solving physics problems. It certainly helps when you can't visualize it in your head. Okay, so what I'm going to do is I'm just going to, because we don't need this big picture of the rocket, all we really care about is what the top of that rocket is doing. And we can represent the top of that rocket by those red dots. We don't need anything else. We just care about where those dots are at a given time. And what we can also do is draw a axis on this diagram. So I'm just going to draw this line here. Okay, now generally, a convention, anytime you have an axis in the vertical direction, we denote it with as the y-axis. Horizontal will be the x-axis. Okay, so let's do something different. What we're going to do is we're going to take this. What we're going to do is we're going to take this, and we're just going to cut. Actually, we're going to take this and I'm going to rotate it. Often it's easier to deal with things which are in the horizontal direction. Okay, and I'm going to move this down onto a new page down here. Just give me a minute to set it all up, and I'm going to make it bigger. Oops. I shouldn't have made it bigger. Okay. Make it a little bigger. There we go. Okay, now, as I said before, we really don't care about the rocket or the picture. We just care about these red dots. So what I'm going to do is I am actually going to try to get rid of more of this picture. So if you just bear with me a little bit longer, let's just clean this up a little bit more. There. Okay, so let's draw the motion diagram now for this rocket. And I've cut back most of the rocket because what I really want to focus on are the positions of the position of the top of that rocket at any particular point. You can also just represent the dots as the rocket itself. So to the right we have the y-axis, and this point right over here is we'll set that to be y equals 0 when the rocket hasn't left the ground yet. So that we'll call that y0. And then here we'll have y1, y2, y3, y4, y5, and y6. So these are representing the position of the top of the rocket at various times. And the time intervals are all the same. So initially we're at t equals 0, and then t equals 0.5 seconds, then t equals 1 second, t equals 1.5 seconds, t equals 2 seconds, and so on. There. So that is the start of our motion diagram. We have an axis. We have plotted position of the object, which are the red dots. And what we can now add to the motion diagram is the direction of velocity. And I will do that with some blue vectors. So initially, the velocity is 0. So at t equals 0, the velocity is 0, which will represent by that triangle there. Then, as we move to y1, our velocity increases, and as we go from y1 to y2, it increases some more, and so on. I can draw all of these velocities. The key point here is to note that the velocity is equal to the change in position, or rather the displacement over time. And as you can see, since these dots represent equal time intervals, the displacement is increasing while the displacement in each time interval is getting larger and larger. So our velocity is getting larger and larger. The equation, if you remember, for velocity is in one dimension is the change in y over a change in time. So you can see, for instance, between 1.5 and 2 seconds, the change in y is smaller than between 2 and 2.5 seconds. Okay, so these are my velocities. We'll label them. This is v naught, v1, v2, v3, and so on. Oh, these are vectors, by the way. And v5. I did two v3s. Alright, let me just fix that. Okay, so these are our velocities. Now, what can we infer about the velocity? Well, we know, if we go back to our velocity versus time graph, the velocity is not constant. It's changing. It's increasing as this rocket accelerates. So this is actually, and because the velocity is linear, we know that the acceleration should be constant. So this is motion with constant acceleration. So let's go back to our graph. We want to indicate the acceleration here. So let's recall what acceleration is. Acceleration, it's a vector quantity. It's equal to a change in velocity over a change in time. Okay, so what can we do with this? Well, let's look at a specific change in velocity. We'll consider the change here, the difference between v6 and v5. So let's just copy that. We will bring it down, and I'm going to make it a little bigger just to illustrate a point. Okay, so there are our two vectors. Remember, a vector, it has magnitude and direction. You can see that v5, because it's shorter than v6, it has a smaller magnitude, but both of these velocities are in the same direction. Now, let's go back to our acceleration. So we can represent a change in v as in this, for this particular interval, is v6 minus v5. And our time interval is delta t. It's going to be a half a second. Alright, now when we subtract two vectors, we can take the second vector, so v5. I just want to take the arrow, so let's copy that. And oops. And what we'll do is we'll rotate it. Just like that. So when you subtract a vector, you're actually adding a vector in the opposite direction to what we had. So this vector that I've just drawn is going to be v5, but negative v5. So if we add v6 and negative v5, what we're left with is this vector over here. Let me just draw it in red. So this vector in red is our delta v, which is not 5, it's v6 minus v5. So that's the direction of our acceleration, and we know already, because of our velocity versus time graph, the acceleration is constant. So this is the direction of our acceleration at every time interval. So we can actually draw that on the motion diagram. So we have motion with constant acceleration. We can just draw the same acceleration vector at every time. I'm trying to draw those of equal length, but it's not quite perfect. There. So this is our acceleration versus, this is our motion diagram for this rocket. And here, all of these accelerations, they're all the same, even though they might not have been drawn all the same. That's just my poor drawing. Okay, so that's motion diagrams, and we can do this with anything. This doesn't have to be a rocket. It could be a car which is accelerating. It could be a ball that is dropped. It could be something that's moving in two directions, not just one. Well, sorry, moving in two dimensions and not just along a particular axis. So this is, hope this was helpful, and stay tuned for another video.